Hello and welcome to the last part of my session, hierarchical clustering. Now, as we already discussed, in hierarchical clustering, a data point belongs to more than one cluster, and a hierarchy of clusters is obtained. It produces a set of nested clusters that can be organized as a hierarchical tree. And this hierarchical tree can be easily visualized as a dendrogram. Now, what is a dendrogram? A dendrogram is nothing but a tree-like diagram that records the sequences of merges and split. Let me explain this to you. Now, if you see in this particular example, we have six data points. 1, 3, 2, 5, 4 and 6. Six data points. Now, let's say the first two data points to be merged to form a cluster were 1 and 3, making a cluster 1. The next two data points to be merged were points 2 and 5, making cluster 2. Now then, cluster with points 5 and 2 was merged with point 4 to make cluster 3. And then cluster 3 was merged with cluster 1 to make a cluster 4. Finally, this cluster 4 was merged with data point 6 to form cluster 5. Now all these sequences of merges have been recorded in my dendrogram, which is here. If you see clearly, first 1 and 3 were merged to form a cluster. Then 2 and 5 were merged to form the second cluster. Then the cluster of 2 and 5 was merged with 4 to form the third cluster. This third cluster of 2, 5 and 4 was merged with 1 and 3 to form the fourth cluster, and this big fourth cluster was combined with point 6 to form my final cluster, cluster 6. Now this is dendrogram recording the sequence of the merges. Now there are various types of hierarchical clustering. Two basic types. It could be agglomerative or it could be divisive. Now, when we're talking about agglomerative hierarchical clustering, it basically starts with points as individual clusters. And at each step, we're going to merge the closest pair of clusters until only one cluster or k clusters, whatsoever we need, k, are left. So all the points are initially just individual clusters, and then we keep on merging closest pair of clusters until we are left with just one cluster. That is agglomerative, aggregation for us. On the contrary, in divisive, the entire process is opposite. We here start with just one cluster containing all the data points. Each step, we will split the cluster into smaller and smaller clusters until an individual point remains. Each of the clusters have individual points, or there are k clusters, whatever k we point. So this is divisive, the opposite of agglomerative. Now, what we are going to do is study the algorithm of agglomerative clustering. In agglomerative clustering, we first compute the proximity matrix. So proximity matrix is distance of all the given points or the proximity of all the given points from all the other given points. I'll show you what a proximity matrix is. Now, as we discussed in agglomerative, we let each data point to be an individual cluster. Then we're going to repeat these steps until only one cluster remains. Now what is that one cluster? What are these steps? We merge the two closest clusters, and when we merge the two closest clusters, the task we need to do is we need to update our proximity matrix. Now this proximity matrix needs to be updated so that we can reflect that which are the two clusters which have been merged, and whatever this new merge clusters, what is the proximity of this new merge clusters from all the older clusters. So we need to reflect the proximity between the new clusters and the original clusters. So the key operation in agglomerative clustering is the proximity, the computation of the proximity. Now, different approaches are present to define the distance between clusters, and we are going to distinguish agglomerative clustering algorithms on the different algorithm which for defining the distance. Now, as already discussed what a dendrogram is, once an agglomerative method is run, the result is generally drawn as a hierarchical structure which we know as dendrogram. Now, this is a tree where leaves correspond to the instances, and these are grouped in order in which they are merged. Now, these are grouped in the order in whichever they are merged. The tree can be then intersected at any level to get the number of groups we want. So if I wanted just three clusters, so my three clusters would be 1, 3, 2, 5, 4, and 6. So I can cut the tree at whatever desired level I want. If I want 4 clusters, my 4 clusters would be cluster with 6, data point 6, cluster with data point 4, cluster with point 1 and 3, and 2 and 5. So I can cut this tree at whatever level I want. Now, initially, we start with clusters with individual points and a proximity matrix. So these are my various individual points, howsoever many number of points I have, and this is my proximity matrix. Now, if you see clearly, whatever the number of points I have, they have been represented into rows as well as columns. So here I am going to record the proximity between point P1 and P1. Here I am going to record the proximity between point P1 and P2, P1 and P3, P1 and P4, P1 and P5. So it is going to basically record the proximity of each point from each other point. Obviously, the proximity of the point to itself would be 0. Okay. So next is, after applying some merging step, we're going to get some clusters. So after applying a few merges through agglomerative, let's say I've got these 5 clusters. Now the, the matrix should reflect that I have now come from points P1 to, let's say, P10 from the 5 clusters C1 to C5, and it should reflect the distance of C1 from C1 to C1, C1 to C2, C3, C4, and C5, and so on. So basically, we would like to merge two closest clusters and update the proximity matrix. Now let's say, if you can see here, the closest clusters for us are C3 and C5, and I want to merge C3 with C5. So I merge C3 and C5, and whenever I merge C3 and C5, I should basically remove the rows and columns of C3 and C5, and I should add one new row and column which specifies C3 union C5, because this is what is happening. I have removed C3 and C5 individually as points and made one cluster of that. So my proximity matrix is reflecting this new entry of C3 union C5. So when the two clusters are merged, now this new proximity of, of this new cluster from all their previous clusters, that we need a policy for updating this proximity matrix and computing that. And that particular policy is basically dependent on how we compute our intercluster distance. So there are many methods of computing intercluster distance. The first one is min or single link. The other is max or complete link. Third one is group average. Fourth is distance between centroids. Now let us discuss each one of them. When we are talking about min or single link, it computes the proximity as the smallest distance between all possible pair of elements of the two groups or clusters. For similarity, higher values indicate closer points. As we already discussed, similarities are higher the better, distances are lower the better. So it is determined by one pair of points, that is one link in the proximity graph. Single link corresponds to constructing the minimum spanning tree of the graph. So let's see if there are two clusters, this cluster and this cluster. Min link talks about those 2 points. The proximity is computed as the distance between the two closest points belonging to the separate clusters. So this is min link for me rather than the distance between this and this point, or this and any of the other points. So because these two are the closest, so my proximity is computed as this. So given 6 points, this we are going to do with the help of an example. So given 6 points to be merged and their corresponding Euclidean distance matrix, we need to compute the agglomerative hierarchical clusters. So these were the points, 6 points, and this I have Euclidean distance matrix. So again I am repeating, this is a distance matrix. So again, as we already discussed, distance we need to minimize. So what amongst, if you clearly see this distance matrix, what is the lowest entry in this distance matrix? Please don't say it is 0. It is 0 obviously, but 0 is the distance between P1 and P1, P2 and P2, which is not valid for us. I want you to find the next minimum distance, and it is the next minimum distance is basically the points P3 and P6. If you see the distance between P3 and P6, the distance between P3 and P6, it is 0.11, the minimum. So here the minimum distance between any 2 points is P3 and P6. So first we are going to merge P3 and P6. Then we will update the proximity or this distance matrix. The next one is basically, if you see after 0.11, we'll compute the new matrix, but which is the next minimum value? It is very clearly showing the next minimum value is P4, P2 and P5, 0.14. So after P3 and P6, we will be merging P2 and P5. Now let's discuss how. First 3 and 6, then 2 and 5, then they will be merged amongst themselves. If we are performing min link, this is going to be the clusters, and this is going to be the dendrogram. Now our question is, how did we update the matrix, or how did we compute the distance between the clusters 3, 6 and 2, 5, or any of the clusters? Now if there are clusters 3, 6 and 2, 5, I want to find the minimum of the distances between 3, 2, 3, 5, 6, 2 and 6, 5. So distance between point 3 and 2, distance between point 3 and 5, distance between point 6 and 2, and distance between point 6 and 5. So these values, these 4 values I have taken from this matrix shown here in this slide, and these are the values, and obviously the minimum of these values, because it is min link, is 0.15. So I take the value as 0.15. The height at which the two clusters are merged in the dendrogram obviously would reflect the distance of the two clusters. Okay. Now next one is max or complete link, also known as click. Here, the proximity of two clusters is based on the two most distance points in different clusters. While in min, we're talking about the nearest 2 points in two clusters. Here we're talking about the most distant point in the different cluster. It is determined by all pairs of points in the two clusters. So if you start with all points and singleton clusters, means having one point, and add links between points one at a time, shortest links first, then a group of points is not a cluster until all the points in it are completely linked. That is, they form a clique. So if you see here, the new proximity is going to be computed as the distance between this point and this point, the one that is the largest. I want to clarify here one thing. You would see, ma'am, distance as largest. Now that is the new proximity. Again, while merging, when we will merge 2 points, we are going to look for those 2 points that have the minimum distance. But when we compute the proximity, we have to take it into account whether we have to take the largest distance or the smallest distance. So given 6 points to be merged and their corresponding Euclidean distance matrix, we compute the agglomerative hierarchical clusters. Again, since we are looking for the minimum point, first P6 and P3 would be merged. Then P2 and P5 again, this would be merged. How are we computing the new proximity? So 3,6 is merged with 4. After that, the cluster 3,6 is merged with 4 and not 2,5 with 1. Why? Because distance of clusters 3,6 with 4 is actually the maximum value amongst distance of 3 and 4 and distance of 6 and 4. So max of 0.5, uh, 3 and 4 and 6 and 4. 6 and 4 comes out to be 0.22, which comes out to be 0.22. Distance between 3, 6 and 2, 5 is computed as the maximum value of the distance between 3, 2, 6, 2, 3, 5 and 6, 5. So it comes out to be 0.39. This is the new proximity matrix. So distance between 3, 6 and 1 comes out to be maximum of distance between 3, 1 and 6, 1. That comes out to be 0.23. So after I merge 3, 6 and 2, 5, the next to be merged is the next what we will do is next I'll merge 3, 6 with 4 and not 2, 5 with 1, because 3, 6 with 4 gives me 0.22, which is lesser than 2, 5 with 1. Okay. Now this max or complete linkage, first we'll merge 6, 3, then 2, 5, then 3, 6 with 4, then 5, 2, 5 with 1, and then the whole one, also shown as a dendrogram. Then we need, the next one is the group average. Now the group average is computed as the average pairwise proximities of all pairs of points from different clusters. Okay, so one needs to use average connectivity for scalability since total proximity favors large clusters. And how we are going to calculate the proximity between cluster I and cluster J is actually the summation of proximity of all the points in cluster I to all the points in cluster J divided by the number of points in cluster I into the number of points in cluster J. Okay, so basically I'm going to find the average of all the points, distances of all the points in this cluster to that cluster. So distance this, distance this, distance this, all these pairwise distances divided by the number of points in cluster this, these are 3, again into the number of lines in this cluster, which are again 3. So given 6 points to be merged and their corresponding Euclidean matrices is the same question. If we are to do it using group average, again we will first merge P6 and P3, then we'll go for P2 and P5, and if I need to find out the distance between some of the clusters, let's say I want to, there is a cluster 364 and a cluster 1. So and I want to find out using group average the distance between the updated proximity if I were to merge 364 with 1. So it would be the distance between 3 and 1, distance between 4 and 1 plus distance between 6 and 1 divided by the number of points in the first cluster, which is 3, into the number of points in one cluster. So taking out the values, it comes out to be 0.8. Similarly, the distance between 2, 5 and 1 can be computed as the distance of 2, 5 2, 1 and distance of 1, 5. See, it is wrong here. Please correct. It will be the distance of 2, 1 and 5, 1. Okay. Divided by 2 into 1 comes out to be this, and this similarly this one. So if we were doing hierarchical clustering using group average, the clusters made in the same data on the data would be this much. Now all the three we have discussed so far, if you will check the dendrogram, they're all three are different. So this is all for today. Thank you so much for being patient listener. Hope you like the session.